exponential growth and decay, this is the most important stuff from the exponentials material. IB is going to test you on your use of these skills, your use. Now, good news is a lot of this stuff is calculator based. The bad news is that means you have to really know how to use your technology. So I already have my graphing calculator. I had my graphing calculator fired up. Let me turn it back on. Earlier my computer was bogged, so I had to shut it off. All right, real world situations can often be modeled using exponential functions, and this is either with growth or decay. Now the other pictures that I showed you, the ones that point down, yes, we can transform those graphs, but those don't really represent things in the real world. However, exponential growth, whose horizontal asymptote is the x-axis, or exponential decay, again, whose horizontal asymptote is the x-axis, they're very, very useful to us in real life. We're talking about modeling radioactive decay, growth of bacteria, loans, interest, things like that. All of this stuff, real world growth and decay. And these are the two equations for that, growth or decay. The A value at the beginning represents the initial value, A, initial value, or initial amount, or something like that. R is rate. R is rate. And T represents time. So we use T. Because again, it's real world, so it's usually over periods of time. R, when you talk about rate, is never a percent, ever. It's always a decimal format. So if I say 10%, you use 0.1. Okay? So when we were graphing these things, we were dealing with this setup. Y equals AB to the x. Correct? Okay. Well, A is still A. And instead of x, we use T. And what we're saying, so I should have written a capital A, but whatever, you get A as A. For us now, the base has been replaced with, instead of a number B, it's been replaced with 1 plus or minus some other number. That means every exponential function that we've done so far could have been represented as 1 plus a number or 1 minus a number, giving us our growth rate or decay rate. Okay. For example, let's say the exponential base is 1.5. That is 1 plus 0.5. Since the base is bigger than 1, that's growth. So 0.5 represents a 50% growth rate. Okay, that's how you would say it. All right. And if the exponential base is between 0 and 1, like 0.8, that is 1 minus 0.2, a 20% decay rate. Cool beans? Cool beans. Great. All right. An entomologist, which is a bug studier, an entomologist is monitoring a grasshopper plague and notices that the area affected by the grasshoppers is given by this equation. Whoa. 1,000 times 2 raised to the 0.2 n hectares. That's some unit of measure of land. Where n is the number. I'm sorry? That's what we're using. Well, hectares is a metric thing. So it's what they use everywhere except for the States. So n is the number of weeks after the initial observation. N is the number of weeks after the initial observation. So the initial observation would have been after how many weeks? It says n is the number of weeks after the initial observation. So the initial observation is at weeks 0. It says find the original affected area. Oh, the original affected area would imply that n equals 0. So A sub 0, meaning the original amount of affected area, is 1,000, wow, that is not smooth, times 2 raised to the, wow, that is not smooth, 0.2 times 0. Oh, well, anything raised to 0 is 1. So the original affected area was 1,000 hectares. Pretty easy, right? I just told you, the A on the front represents the initial amount. Ta-da! Principal is when you're talking money. But yes, since these aren't specifically about money, but yes. It says find the affected area after 5, 10, and 12 weeks. Guess what we're going to do? We're going to plug in 5, 10, and 12, and we're going to ask a calculator. This is for part A. So part B. Sorry about the writing being so jagged. The computer is struggling today running my screen recording program for some reason. I don't know why, so it's really bogging down the processor. So it's having trouble keeping up with me. That's why everything looks so jagged. Part B, BI, I guess, plug in 5. So A sub 5 is 1,000. Oh my gosh. Okay, write very slow. Write painfully slow. Times 2 raised to the, oh my gosh. Drew wants in. Yay, Drew, come on in. 0.2 times 5. Which is 1. That's 1,000 times 2 to the 1. Or 2,000 hectares. I wonder if it's the graphing calculator. Let me shut that off real quick. We'll have to fire it back up later. I'm just going to try to turn some things off to give myself a little bit more computer brain power. Part 2. That's what was doing it. Look. Wow, that's incredible. All right, for some reason, running the screen recorder and the calculator at the same time is just too much for this piece of technology. You're going to plug in 10. You're going to get 1,000, so A sub 10. Oh yeah, much better. 1,000 times 2 raised to the 0.2 times 10. And you see why I'm showing this work? I mean, the reason why I'm showing this work is in case I fat finger a calculator, and this was one of those IB questions that's only worth 2 marks. You want to show your work in case you can get a method mark. But anyway, that gives us 1,000 times 2 to the 2. 2 to 2 is 4. So this is 4,000 hectares. And the last one is 12. I'm not even going to pretend to tell you what 2 to the 2.4 is because I have no clue. But that's what calculators are for. 1,000 times 2 to the, I'm just going to say 2.4. So I'm getting lazy here. We grab handy dandy copy of my notes from last year so I don't have to do this math by hand. You should get 5278.03. There. And then C says to draw a graph. But that just means, why don't you just plot the points you just found? I mean, you just found 4 coordinates. Plot those bad boys. Now, this represents a real-world situation. So what is my domain? Zero to infinity, including 0. Negative time makes no sense at all. Remember, n is the number of weeks that we're covering. So our graph had better not go to the left of the y-axis because that would just mean negative time. And these are not time-traveling grasshoppers, folks. So what do we do? 2, 4, 6, 8, 12 is what I did. 2, 4, 6, 8, 10, 12, I should say. I can count. And my y values. The smallest one was 1,000, and the biggest one was over 5,000. So I'm going to go by thousands and just go to 6,000. 1, 2, 3, 4, 5, 6,000. Whatever. You could fill them all in if you want to. Screw it, I'll just put them all in there. Okay. Great. Our initial value was at 0 weeks, was 0, 1,000. And then we got 5, 10, and 12. Well, at 5, we found 2,000 hectares. That's here-ish. At 10, we got 4,000 hectares. I'm going to get in your way for a second so I can line these up. There we go. And at 12, we got about 5.25 thousand. So if I had to guess, it looked like that. The point is the graph does this. So you can see it does have an exponential growth curve to it. Should be very, very, very easy to work with. You know what? It's not part of the notes. What time do we get out of here? It's not part of the notes, but I think it's worthwhile to do real quick in case it's an IB style question. I don't know if I've ever seen one like it, but I do this for my Algebra 2 students, so I might as well do it for you guys. The way that this equation is written, 1,000 times 2 raised to the 0.2n, does it fit the mold of growth the way it's written? Does it look like this? No, it doesn't. You know what the problem is? Two things in the exponent. That's a problem. So what do? Remember, a power to a power, you multiply those exponents, right? So we could have written it like this. And then you would have to grab a calculator and figure out what 2 to the 0.2 is. I'm not even going to pretend to know. 2 raised to the 0.2 to 3 sig figs is 1.149. 1.149. So if I was asked from IB, what is the growth rate? R equals 0.149 or 14.9% growth. Because the thing inside the parentheses is either 1 plus R or it's 1 minus R. It's clearly 0.149 more than 1. So it has a growth rate of 14.9%. Cool? Now it fits the mold. Now, of course, that's a rounded exponential base, but that's kind of what we have to do. Okay. That wasn't in the notes, but it is definitely worthwhile. All right. Now, the next question, I was going to use my graphing calculator, and I'm still going to. It's just going to make my writing kind of choppy. So I'm not going to turn the graphing calculator on until I'm going to use it to solve. That way I can take notes without looking like caveman is chiseling. Waiting for the board. There we go. When a diesel electric generator is switched off, the current dies away according to the formula I of t. So my physics people, I of t, current, yeah, equals 24 times 0.25 to the t amps. Again, this is not part of the notes, but this formula could have been represented as 24 times 1 minus 0.75 to the t, which means this thing has a 75% decay rate. It's just worth saying. Anyway, 24 times 0.25 t amps, where t is the time in seconds after the power is cut. So we've been told to find the current. Is it current? Yeah. The current after 0, 1, 2, and 3 seconds. And you legitimately just plug it in. 0, 1, 2, 3. So for part A. Bless you. I of 0 is the initial amount. Please don't ever work for this. It's the number on the front. That's the initial amount, as long as the exponent is a simple variable. If there's anything else up there, you got to plug it in. But so that's when t equals 0. When t equals 1, 24 times 0.25, that means 1/4 of 24. 4. 6, I can math. 6, yeah. I of 2. The current after 2 seconds, 24 times 0.25 raised to the 2. Grab handy dandy calculator. And you're going to get 1.5, exactly 1.5. And of course, this would be on a calculator portion of the test. And your test would obviously, this chapter, have probably a calculator and non-calculator portion. Okay. And the last one is what's going on after 3 seconds. 24 times 0.25 raised to the 3. Holy cow, no clue. Calculator told me. It's 0.375. Well, part B is kind of a trick question. What current flowed in the generator at the instant it was switched off? Instant switched off represents time equals 0. So this would be like, command would be like, write down the amount of current that flowed at the instant it was switched off. And you just go 24. We amps? I wasn't paying attention. It's currents in amps, right? Yeah, okay. C says plot the graph. And this one actually says when t is greater than or equal to 0. That's because, negative time. Again, we're not time traveling here. You just plot the 1, 2, 3, 4 dots that you have right there. Pretty simple. And I use time equals 1, 2, 3, 4. And I went by 5s on my Y scale. So 5, 10, 15, 20, 25. It's just a sketch. And it says to plot them. At time equals 0, you've already said 24. That's here-ish. And then at 1, it was at 6. So it cascades down pretty quickly, but that should make sense. I mean, like power, right? It had power, now it has none. We all like to think that it's instantaneously 0, but it's not. Then after 2 seconds, we had 1.5. Whoa, boy, that's way down here. I mean, fat dots, right? And at 3 seconds, it was essentially nothing. What? Not equal to 0, just essentially. Basically, here's what you got. Whoa. Mathematically, will there ever be 0? No.
That's crazy.
In real life, of course. I mean, let's be real. I mean, but mathematically, there will never be 0.
So how does that work? What's that talking about the value?
It's talking about how much current is still remaining in the generator. I mean, I don't know. Look, I'm gonna be real. I'm not a physicist. So, is there ever 0 current in real life? I actually don't know.
No.
There's. Yeah, but I mean.
A lot of the time, you'll just say, physically no.
Physically no. Oh, okay. What's the last one?
On paper, you can, but like if you're writing out a question,
Mm-hmm.
but you could never measure that with a perfect scale.
Yeah, because it's technically, because it's all done through math, and math says, well, it's never going to get there. But part D, we've been told to use a graph or technology to find how long it takes for the current to reach 4 amps. So here's what you're doing for part D. You're asking yourself, when would this happen? And that's what you would use the graphing calculator for. So I'm going to try to attempt to turn it back on without crashing ActiveInspire. And through the magic of pausing the video, the graphing calculator is, oh my golly, that is the wrong window. You go back to where you came from.
This is like when there's a mirror.
Yeah, infinite screens. There we go. Darn it. Oh, what? Whoa, do you see that? You don't see what it's doing? It's refusing to go to the screen on the right. Okay, well, whatever. There, I forced it. Oh, man, that's crazy. Okay, so y1, that's our equation. And our equation was 24 times 0.25 raised to the, and of course we're using x, but you get the idea. And the horizontal line that we were trying to hit was y equals 4. Now we're going to have to play with our window. I mean, those y values got really small really fast, didn't they? So window. So you go to window. X minimum, which represents time, well, they already told you is greater than or equals 0. So you're going to start at 0. We know for a fact that that value of 4 happens between time equals 1 and time equals 2. That's because at time equals 1, we had a y value of 6, and at time equals 2, we had a y value of 1.5. So we know what happens between time equals 1 and time equals 2. Okay, so my x max, does it need to go all the way to 10 seconds? No. Why don't you just take it to like 3 seconds? This way your answer is going to happen somewhere in the dead middle of the x's, because we know it's going to happen between 1 and 2. And the scale, you want to go by 1? Sure, whatever, who cares? The y minimum, well, it's 0, because technically that means 0 electricity. And the maximum, well, yeah, you're looking to try to figure out where it hits the number 4. So, yeah, I mean, you can go to 5, 6. 6 sounds good. Let's go to 6. And a scale of 1, whatever, and just hit graph. Come on, blue curve. There you are. And then red line. There you are. And we're just looking for an intersect. You know what I'm not going to do? I'm not going to spend the time to solve this by hand algebraically. It's not worth it. Let your calculator do the job when you're taking a calculator test. You're going to get the same amount of credit. Second, trace, you're looking for an intersection, so second trace intersect, 5. Since I only have 2 things graphed, it says, is this the first one? I go, yes. It says, is this the second one? I go, yes. And it says, hey, why don't you take a guess? And I'll just scroll to the left until I'm pretty darn close to the answer. And I go, give me that answer. Give it to me now. It says about 1.29. 3 sig figs, about 1.29 seconds. 1.29 seconds. And I am going to now turn this graphing calculator off because it's hard on my computer. 1.29 seconds. So part D happens at around 1.29. IB doesn't care about the units because everything was in the same units, so you don't have to worry about it. This is not physics. I know in physics you get in big trouble for no units. In math, they're just like, yeah, whatever. The only time you have to worry about it is when the question's asked in one unit type, when the word problem or whatever was given to you in a different word unit type. That's the only time you have to worry about it.
On the calculator portion of the test, would we ever have something other than write down?
Oh, yeah, it still says find. It's usually worth 2 marks-ish. Sometimes it's worth 3. Writing that the 2 things are equal to each other gets you 1 of those marks. But then just writing the answer after that would get you the rest of the marks. Yeah, but don't ever say write down the point of intersection, because write down means it requires no work. The weight of radioactive material remaining after T years is given by this equation. Notice what's missing. A, or the initial amount, right? Part A says find the original weight. Doesn't the original weight imply that no time has passed? Right? So this is at, come on now, this is at time equals 0. So the initial weight is the initial weight, wait, what? Times 2 to the 0, which of course is just, oh, the initial weight. It's literally just W sub 0. This right here. This is the initial weight. Yeah, I didn't have to actually write down any of that work. Because if you understand that W sub 0 means the weight when no time has passed, you just write, oh, W sub 0.
But that's just the letter.
Right, but
if I were to read that, I would actually think that I need a number.
Right, but here's the thing. It doesn't matter how much you start with. The rate of decay will never change. It's one of those trick questions, so which you'll see in just a second. Like part B says, find the percentage remaining after 200 years. A student that doesn't understand exponentials goes, but I don't know how much I started with.
Well, no,
No, I'm not saying you. And they go, but a student that does understand exponentials understands that it doesn't matter how much you started with, because the time it takes to double or triple or cut in half or cut into fourths is always the same because it's exponential. So for part B, it says find the percentage remaining after 200 years. And you go, okay, W sub 200 is W sub 0 times 2 raised to the negative 0.001 times 200. And what you're going to get is, and you would just use your calculator to get this number, W sub 0 times 0.8706. That means you have 0.8706 of your W sub 0 left. So that is about 87.06% remaining. So instead of saying times, you can say of. Oh, I have 0.87 of my W. I have 87% of my W remaining. You mean cool.